Østerild is a prime location due to the vicinity of the sea. You have very good winds in this part of Denmark. When you have a blade that is 75 meters long, the tip of the blade is running at 200 kilometers per hour. Blade design today is much more comparable to, let's say, a Formula One team or aerospace design. Every time we do something new, we really push the boundaries for what's possible.
A global industrial revolution is underway.
Yes, we have a technological challenge for our environment, for the well-being of the population of the planet, for civilization.
Driven by passionate, dedicated individuals intent on shaping a new world.
I do it because I look at my kids, and I honestly am convinced that this is the way.
A cleaner world.
There is a way forward other than burning fossil fuels out of our funnels.
A greener world.
This wind farm is producing more hours of power into the grid than all wind farms in the UK and probably in the world.
What we've done in the past is not going to solve these challenges. We need to find new ways, and I think the only way to do that is to bravely step forward and implement technology.
Together, they are pushing engineering to its limits to create extraordinary machines that can protect our planet for the future. The world is entering a post-carbon age, and one of the most visible signs of that is the wind turbine. Like it or not, these gentle giants are slowly becoming a part of the modern landscape. Today, there are over 300,000 turbines around the globe, generating 600 gigawatts of electricity, enough to continuously power nearly 400 million homes. And now, hungry for more clean energy, countries are looking to their coastlines. But building wind farms at sea is much harder than on land.
The forces on the steel are so big that the turbine will actually destroy itself.
We've had gusts up to 100 miles per hour of wind speed and waves up to 8 meters.
Yet the rewards could be world-changing. Unlimited amounts of clean energy could replace fossil fuels for good.
These turbines will produce enough clean energy to power 630,000 homes.
Offshore wind has so much potential for the electricity system of the future.
Can we actually make all the world oceans available for wind power? That was the challenge.
Engineers are racing to design taller turbines, bigger wind farms, and structures that capture the wind over deeper oceans. Because if they can harness even a fraction of the ocean's wind, they could supply all the world with electricity. The only way to harness wind power that we know of is with turbines. Wind is simply air moving from one place to another. And when things move, they have energy. But turbines can't capture it all, because as you take energy out of the wind, the air slows down. If a turbine took 100% of the energy, the air would come to a standstill just past the blades. And that stationary layer of air would block any more wind from blowing through the rotor. In fact, scientists have worked out that the most energy it's theoretically possible to capture is 59.3%, known as the Betz limit. So engineers want to get as close to that limit as they can. And the best way they currently know is to use airfoils. Just like the wings of an airplane, this teardrop shape creates lift which is a force perpendicular to the movement of air across it. Some wind turbines can now capture almost 50% of the wind's power, and they're still improving. The blades are vulnerable to storms, so when the wind blows too hard, the pitch changes to let it rush harmlessly past. In good conditions, the rotor turns a shaft inside the nacelle, the hub at the top of the tower that houses the generator. Here, a ring of magnets is turned around a metal coil, which generates electricity. These modern wind turbines were well established by the end of the 20th century, but they were still small and expensive. Yet, the problem with burning fossil fuels was gaining attention.
People started looking at alternative means of producing energy, not just actually because of climate, but because fossil fuels were finite. And so the energy sector 20 years ago was really starting to get to grips with this concept of an energy transition, completely changing the way we produce power.
Wind turbines spread rapidly, but the size of available sites was limited, and many considered them a blight on the landscape. A few pioneers could see a possible solution: building wind farms at sea.
Offshore, you were able to capture far more wind and produce far more power. And the scale that you could achieve offshore is much bigger than onshore because you're not so close to towns and cities.
But the harsh conditions at sea are daunting, and many wondered if offshore wind farms were feasible at all.
There were big questions about whether the technology was going to be reliable enough and survivable enough out in these really hostile offshore environments where you naturally have to put the turbines to catch the wind. And also big questions about how expensive it was.
Jonathan Cole, managing director of offshore wind at energy company Iberdrola, was determined to find a way.
Myself and a small team of people got together to develop a strategy to get into offshore wind. And what we could see was that if you could get the scale and the industrialisation into the offshore wind sector, it had huge potential.
Jonathan's vision was for massive wind farms at sea that could replace entire fossil fuel power stations, and to eventually supply the world with clean wind power. But to do that, he must bring down the high cost of offshore wind, enough to compete not only with other renewable energy sources, but with coal and gas. In 2010, Jonathan started planning a vast wind farm to prove it could be done, and the UK was the perfect place to build it.
There were a number of large gas and coal plants that were going to have to shut down, and so the UK had to effectively rebuild more than half of its energy infrastructure. And of course, the UK is an island with huge quantities of shallow water seabed off the island, very windy seabed. So it was a really unique place in terms of really needing the power, but also having this amazing resource right off the coast.
The proposed offshore wind farm was named East Anglia 1. It would be far bigger than any in existence at the time. Building such a colossal array posed huge challenges to Jonathan's team. They needed far more powerful turbines than any on the market, and structures to hold them above 45 meters of turbulent water. They needed 102 of these giant turbines spread over an area of 300 square kilometers, and they had to find a way to transmit the electricity 50 kilometers to shore. This vast wind farm would provide more than enough power to replace a typical coal-fired power plant. And Jonathan must achieve all of this while also lowering the cost.
We put teams of people in place to make sure that East Anglia wasn't just going to be the biggest project in the world, it was going to be the most cost-effective as well.
April 2017. At shipyards in Spain, Northern Ireland, and the UAE, hundreds of metalworkers began building the foundations called jackets. These towers hold the turbines above the water, and they're securely fixed in place by long piles driven deep into the seabed. The structures must be extremely strong to not only hold turbines weighing over 400 tons, but they must also withstand stormy seas and absorb the huge load from the wind. To drive down costs, Jonathan hired Charlie Jordan as project director. Charlie knew that these bulky frames were not only expensive to make, but also to move around.
A big element of the cost is transportation and the storage of these structures. What we sought to do is to try and reduce the cost, and one area of innovation that allowed us to do that was reviewing the jacket design.
Jackets normally have 4 legs. Charlie's team realized that if you removed one of them, you could fit more jackets on a barge, which would lower the cost of transporting them. But it would also weaken the structure.
To just change from 4-legged to 3-legged, the structure would then be too slender because you have these additional loads that's got to be transmitted through 3 legs as opposed to 4. So what you've got to then do is look at the design, the strengthening.
The solution lay in a neighboring shipyard, which was making the piles that would ultimately pin each leg to the seafloor. Each pile is made up of 19 individual steel cans laid end to end and weighs 120 tons. The engineers calculated that making the piles around 150 millimeters wider would transfer the extra load to the seabed, making the overall structure strong enough. The enormous jackets could be built with 3 legs after all. As the workers assembled 845 tons of steel, each immense tower steadily rose to stand 65 meters tall. In Spain alone, over 1,000 people worked on the foundations for a total of 1 million hours. To complete the structure, one final component was needed that would ultimately connect the jackets to the turbines. These rings of steel are called flanges. They have to be extremely strong and also precision engineered. But to make a ring of steel strong enough to hold the weight of a turbine, the components had to be forged at high temperatures. And that made it much harder to get the size exactly right.
Steel by nature, when we're heating it up and then it's cooling down, has the likelihood of expanding and contracting. So it's very important that going through the fabrication process, we make sure that there's precision engineering to make sure that these things are designed with millimeters of tolerance.
To forge the huge rings, the team had to heat the steel to a temperature of over 1,000 degrees Celsius. Then they rolled and machined the steel. The flanges must have a diameter of exactly 6,002 millimeters. But metal shrinks as it cools, so the technicians had to get their calculations exactly right, first time.
The team did a fantastic job in making sure that when we join the foundation to the wind turbine, there are no gaps and we've got a good solid connection.
Within a year, the foundations were ready to be shipped to the North Sea. As planned, the 3-legged shape allowed more jackets to stack together on the barges.
By doing it 3-legged, it gave us tremendous advantages, mainly in terms of the space that it took up. So for storage, for transportation, for then taking them out in installation, we're able to carry more jackets on a single trip.
With some of the barges being sent 19,000 kilometers round the southern tip of Africa, every journey saved added up. Charlie had his first big cost savings, and the jackets were on their way. The team could now install the foundations in the North Sea. First, they lined up the load-bearing piles and hammered them down into the seafloor. Then they lowered the jackets on top to be fixed onto the piles. The foundations were now ready for the wind turbines. Meanwhile, the team had to build a structure called an offshore substation. This massive machine would sit in the middle of the wind farm, where it could collect all the electricity generated by the surrounding turbines and send it to shore.
The offshore substation could effectively be described as the heart of the offshore wind farm. Here you've got all the individual lines, or it could be like the arteries where all the turbines are connected.
At East Anglia 1, the substation would have to increase the voltage to over 200,000 volts, then send the electricity along the seabed and underground to an onshore substation, where it will connect to the grid. The high voltage allows more energy to be transmitted and means less is lost as heat along the way. But to handle an offshore wind farm bigger than any other, the team needed to build a substation like none before.
We wanted to be having a wind farm that produced as much green energy as it possibly could. But a key function of that was then the design of the offshore substation. So similarly, we looked to maximise the size of that offshore substation as big as we could technically make it.
By summer 2017, construction of the super-sized substation was well underway in Spain, as well as the gigantic jacket to hold it above the water. At nearly 4,000 tons, it's the largest of its kind ever built, which created challenges.
I think we're looking at possibly 2 vessels available in the world to be able to install such a structure. So actually, before we'd even started with the substation, we had to book the vessel. And what that meant was we then had to book the vessel 3 years in advance for a 2-week slot.
If the schedule slipped and they missed their slot, it would lead to delays and more costs, so everything had to go according to plan. The first component to be sent to the English coast had to be the jacket foundation. But as the structure left the port in Spain, there was an obstacle in the way. The bridge in Cadiz is over 3 kilometers long and 69 meters high. But despite being one of the tallest in Europe, the foundations on the barge reached even higher.
Immediately when you come out of the port, you've got a road bridge there that, under normal tides, the substation wouldn't actually fit under.
There was only one solution. To clear the bridge, the team had to hit the brief window of low tide exactly.
From a distance, you watch this massive structure sailing under the road bridge with a very limited clearance. It was certainly a very exciting point of the project.
Hot on its heels, the world record-breaking substation is also loaded onto a barge, ready to install at the heart of the wind farm. The giant powerhouse left Spain on a 2,000-kilometer journey around Portugal and through the English Channel to its new home in the North Sea. And they were bang on time for the giant crane vessel. The installation could begin.
These are enormous vessels at nearly 10,000 tons, and these vessels themselves are at nearly 200 meters long. The substation itself at nearly 4,000 tons is an enormous structure to lift.
Despite the crane vessel's size, the weight of the suspended substation would still be enough to tip it over. So, to balance it out, 30,000 tons of ballast was added to the ship's hold, 3 times the weight of the Eiffel Tower.
When you start to design the lift, there's actually not just the arrangement of the substation, but you actually have to orientate and rearrange the vessel itself with ballast in order to support the lift.
The substation was finally in place. Next, it had to be connected to the grid in England. So, an 85-kilometer-long cable was laid along the sea floor. Then, coastal cliffs were bypassed with a tunnel to carry the power line, followed by 37 kilometers of trenches to connect with an onshore substation. Here, the electricity from the wind farm would join the national network. Finally, everything was ready for the turbines themselves. When the team were planning East Anglia 1 in 2010, the biggest turbines installed anywhere in the world could produce 5 megawatts of power. Enough to fully charge 3,000 typical electric cars every day. But to make cheaper electricity, they needed even more powerful turbines. And that meant much bigger rotors than were available at the time.
At the time we chose the wind turbine for the East Anglia 1 project, it didn't even exist. It only existed in paper, and it was bigger than anything anyone had ever seen before in the renewable energy sector globally.
Once they placed the order, it was up to a team in Denmark to find a way to make it. Oosterilde, Denmark. On a windswept plain near the North Sea stand some of the biggest wind turbines in the world. Despite being on land, these giant structures are designed to eventually be used at sea. As offshore wind turbines get bigger and bigger, this is where they come to be tested in the real world, including the turbine destined for East Anglia 1.
Even though we have very detailed computer modeling used throughout the whole design phase, from the early concepting to the detailed design in the end, it can only get us that far. We still need to test in real life.
Jeppe Funk Kierkegaard leads the blade design division of the world's biggest offshore turbine manufacturer, Siemens Gamesa. In 2015, they had to provide that the turbine would generate as much electricity as they'd promised it would. And the margins in the wind industry are extremely thin.
The worst case scenario is if the turbine performs 1 or 2% less than what we promised, because that would completely change the business case for our customers and for society for the offshore wind farm.
It was Jeppe's job to design a rotor that could generate over 50% more electricity. To make it more powerful, he had to lengthen the blades from 63 meters to a phenomenal 75 meters. But that could have a big knock-on effect on the blade's weight and cost.
While the length only increases 25%, if you don't put in new technologies, the mass would increase for something like 50%. So a heavy blade needs a heavy hub, a heavy nacelle, a stronger tower, all the way down, and that really drives cost. So from an engineering perspective, the real challenge is to keep this exponential growth of mass in check and keep it as small as possible.
Jeppe's team had to completely redesign the blade to be longer without being much heavier. But reducing the weight of a longer blade would make it more susceptible to damage from strong winds. They decided to try a radical new approach.
One of the inspirations that made us change the design are from birds, especially like the seagull, where you have a seagull wing which is flexible and allows it to bend with the forces that are put upon it from the wind. Otherwise, it would break. The effect you want to have is that as the blade bends, it also twists, because that's how it sort of deloads from the wind.
The plan was to design a blade that's incredibly flexible, so that when a strong gust of wind puts a heavy load on it, instead of snapping, it bends. But there's still a danger it bends so far that it breaks. A brilliant tweak to the design makes the blade twist slightly away from the wind as it bends. That twist reduces the load and saves the blade from damage.
That reduction in loads enables us to make the blade longer, basically for the same mass.
Next, they had to build the blades and test if the design worked. Each giant blade is handmade. First, the team lays several tons of glass fiber in a huge mold to give the blade strength. The precise angle of the glass fiber sheets should cause the finished blade to twist. Next comes a layer of balsa wood, which is stiff but also lightweight.
Then we have to inject 8 tons of epoxy resin, so sort of the matrix, the glue that keeps the blade together. The blades we have are actually the biggest one-piece casted structure in the world.
A series of punishing tests proved that the radical new design bends and twists as it's supposed to. But could it generate as much power as they'd promised? Eventually, the 75-meter blades were lifted into place for the first time. The biggest rotor anywhere in the world. Here at the Offshore test site, meteorological masts measured the exact speed of the wind. So, by measuring the power generated at different wind speeds, the team could calculate the performance and fine-tune the turbine. After 3 years, the results are ready. And to Yappe's delight, the turbine has performed beyond expectations by 1%.
While that might not sound like very much, it is actually a very significant upside. Imagine if you have a large wind farm with 100 turbines, you actually get a turbine for free.
The biggest wind turbine in the world has passed its tests with flying colors. Next, it's ready to be deployed at one of the world's biggest wind farms. Great Yarmouth, England. By the summer of 2019, the giant components have come together on this dockside, ready to construct 102 wind turbines.
It's been quite a journey. I've been working in this project for the past 5 years, and it's quite emotional seeing it happening, seeing the reality of it, being here on board of the vessel, witnessing the first load out. We are just reaching the summit of the project. Everyone is eager to see it happening in reality.
The turbines will be among the largest and most powerful ever built. Each tower is as tall as a football field is long. Each blade would outstretch the full wingspan of a Boeing 747. And the hubs, known as nacelles, could each fit 2 double-decker London buses inside.
Here at this port in Great Yarmouth, we're bringing together all the components that will comprise the wind turbines. We've got blades, all 306 of them will be hand-built and brought down here to be loaded onto the ship to be installed. And then we've got the nacelles, which are the real heart of the wind turbine. They've been built in Germany. And then we've got towers that have been manufactured all around Europe, in Spain, in Scotland, and in Denmark. All the components, they've been shipped here, and they're going to be loaded onto this vessel to sail them out to the offshore wind farm and to start building them one by one until all 102 wind turbines are built in the wind farm.
Once fully assembled on its base, each turbine would stand at twice the height of the Statue of Liberty. And at full power, each one will provide over 6,000 homes with continuous electricity.
when this project is complete, all the 102 turbines are installed and commissioned, they will produce enough clean energy to power 630,000 homes.
To install and then maintain these turbines will take a highly trained local workforce, able to master the harsh conditions of the North Sea. In typical winter conditions, survival times in the water can be as low as a few minutes.
Of course, it's imperative that we look to keep everyone safe. Everyone that comes out and helps us and goes into these environments are working in challenging environments.
With the very harsh conditions offshore in the wind farms, working offshore is a very onerous task. They have a long commute to work in the morning.
To keep the team safe, they must plan for the worst. And that means immersive training. Lifeguard Stan Clouting is working with local trainees in Lowestoft, England.
I am very passionate about the subject of looking after people, about touching their life in some kind of positive way. And everybody going home in one piece, should it go wrong, God forbid.
The training pool simulates the wind and wave conditions that the trainee technicians will face in the North Sea. These new recruits will go on to build and maintain the wind turbines in the East Anglia zone for decades to come.
I'm a trainee BOP technician, so it basically involves kind of everything you can really do on a wind turbine, from like areas of maintenance and operations. The whole wind farm's going to last my entire life, so I'll definitely be out there for what I can see lifetime.
Over a 5-week course, the trainees must master new skills and survival techniques to keep them safe in hostile waters. But the most important lesson is to have the right mental attitude.
It's not just about informing them, it's about conditioning them as well to get their mojo turned on, to raise the hackles on the back of their neck, to use controlled aggression for when something should go wrong. So it's the little things we pay lots of attention to, and we will drive them hard.
These trainees will soon be ready to head out safely to the wind farm that's rapidly taking shape off the coast. As the turbine parts head out towards their final destination, everything is on schedule and on budget. The specialist vessel, called a jack-up barge, is designed to plant 4 legs firmly on the seabed 45 meters below, making the barge completely stable, despite the waves. Then they can begin to build the turbines.
Aquí a mis espaldas tenemos el Sea Installer, que es el barco que va a realizar el montaje de las turbinas. Ahora mismo va a iniciar lo que es el izado de la torre y a continuación izará la nacelle encima de la torre. Y posteriormente instalará las 3 palas. Es una operación que viene tardando en torno a 14 horas.
It's crucial that the team keeps on track.
When you're in the offshore installation phase of the project, that's probably when you're at the highest point of sensitivity to delay, because that's when you've got these huge, expensive offshore wind installation vessels out working in the field, and we've only got them there for a finite period of time before they have to go on to their next project. So it's really important that you can keep within the programme that you've set.
Installation vessels cost around $150,000 a day, so any delays will lead to heavy costs. But the team have already installed 13 turbines and are getting into a rhythm.
El barco lleva 4 turbinas completas en su cubierta y cada vez que completa un ciclo de 4 tiene que volver a puerto a recargar componentes. Hasta el momento ha estado funcionando muy bien y no hemos tenido ningún tipo de percance y los tiempos de instalación están siendo bastante buenos.
But as summer turns to fall and then winter, the weather gets increasingly windy, which makes lifting the components harder.
Particular challenges are about the blades. They're 75 metres long in this case, aerodynamically designed to make sure they're capturing the wind. So if there are any gusting winds, you know, the blades will be most susceptible.
In 2019, the East Anglia 1 assembly was set to face one of the stormiest winters on record.
We did experience some real exceptional weather the end of 2019 and into early 2020. I think at one point we had 3 named storms come through in a period of 3 weeks.
To avoid any accidents, all operations stopped when the wind was too strong. But to keep on track, Charlie had a trick up his sleeve.
We were able to introduce a second vessel. So the idea of that was so that we could be installing turbines in parallel with 2 vessels, 100% increase in the capacity, so that when the weather was good and we're in periods of suitable conditions, we could maximise the installation during that period.
By moving fast during the windows of good weather, the team kept making progress despite the disruptions. July 11th, 2020. The final turbine was connected to the UK national grid. Altogether, they generate 740 million watts of electricity, powering over 600,000 homes.
So you spend all this time putting the pieces together and actually seeing bits of it working, but you know, when it comes together and all turbines are operational, everything was working how it's supposed to, it was, you know, a fantastic achievement.
It really was an amazing achievement, an amazing feeling for myself, but for the hundreds of people involved in this project.
The project had finished on schedule and under budget. Proof that offshore wind can generate electricity at a competitive price. With 2/3 of the Earth's surface covered in water, the rise of offshore wind seems unstoppable. But its growth is limited by a crucial factor.
Offshore wind has been really successful so far in delivering in areas where there's an abundance of shallow water sites. But there's a lot of parts of the world, like the west coast of the United States, in South America, in parts of Asia, where they just don't have those shallow sites. And in that case, some other solution needs to be found.
Surveys have found that over 95% of the world's seas and oceans are too deep for jacket foundations. The future of offshore wind may be limited to only a handful of coastal locations after all, unless a completely while air above give buoyancy to pull it up. Floating turbines could be put almost anywhere in the ocean, but would they be stable enough in a storm? Engineer Simon Moxnes was brought in to find out.
My role in the early phase was to run simulations to demonstrate that the structure, the floating structure, actually could survive the worst hurricane conditions that we could foresee out there in the ocean. What we discovered when we ran those simulations was that the rocking motion back and forth, what we call the pitch of the structures, was very big. It was pitching up to 20 degrees, which is quite violently. And we knew that such a standard wind turbine that we intended to use on our floating structure couldn't survive much more than 10 degrees.
To make the structure more stable, the team needed to get the center of gravity as low as possible. So they tried a long cylindrical tank containing very dense ballast. Finally, they found a design that worked, in theory.
We were actually quite inspired and as as happy as an engineer can be.
But for floating wind power to be a success, Simon and his team had to prove that it would work in a full-scale wind farm. 15 years later, after years of testing smaller-scale demos, part of the world's first floating wind farm was under construction in Spain, and the shape had to be exactly right.
If we get a structure that has bumps and bends, then the forces and a crack can create a leak, and a leak will make the floating structure sink.
The finished structures are over 90 meters long, 14 meters wide, and weigh over 2,000 tons. The team loaded the Titanic steel tanks onto ships and sent them to the assembly location 2,000 kilometers away. By May 2017, the floating substructures have arrived at Hardanger Fjord in Norway. Next, the team have to add the ballast. While 2 tugboats hold the substructure in place, a third boat pumps water inside through a hose. But water alone is not heavy enough.
If you use water as ballast, your center of gravity will just not be low enough. And you will get a very floppy structure, and a structure that is not capable of supporting a wind turbine with heavy thrust from the wind.
The water makes one end sink down 80 meters below the surface. Then they add iron ore, which is 5 times denser than water, to lower the structure's center of gravity and make it steadier. Eventually, each structure is weighed down by 5,000 tons of iron ore and 3,000 tons of water, taking the total weight to 12,000 tons, equivalent to 2,000 African elephants. The result is an extraordinarily stable base, ready to hold the world's first array of floating wind turbines. At the nearby port of Stord, all the turbine components are being lined up. The fjord is 900 meters deep and protected from severe weather. But even here, the precise maneuvers involved in building a wind turbine are difficult on floating foundations. Instead, the team first assembled the turbines on land where it's stable, so they can then be joined to the floating bases in one piece. But lifting such large turbines all at once has never been tried before. And there are only 2 vessels in the world large enough to do it.
That vessel is extremely expensive. That means that you can't fool around and use time. You have to just do the job, put it on, and it has to be land in perfect position.
The SAPEM 7000 2 monster cranes are needed to lift the 170-meter tall turbine. This maneuver has never been attempted before and will test the team to their limits. They must proceed with caution. So it takes hours to lift the first turbine out to its base. Monica Pettersson is the assembly site manager.
Det här är helt sikkert. Vi har rört. Vi faktiskt rört. Så mycket som ligger bak.
At the last minute, the crane stops lowering the turbine. Something seems to have gone wrong.
Klart det är mycket krafter så vi vill ju inte. är tungt.
But despite its bulk, this vast ship can move with pinpoint precision. Its state-of-the-art dynamic positioning system uses 12 thrusters to keep the ship fixed in place.
Ja, men vi prövar sig igen nu. Nu ser det fint ut. Tack. Woo! Kul! Fantastiskt. Tänk hur mycket timmar som ligger bakom det här. Tänk! Nu är vi där. Det är på plats. Så bra. Men du, världen, nu har vi bevisat att konceptet fungerar.
After many hours, the turbine is successfully connected to its floating base. A world first.
Nej, det här var otroligt käckt. Det som har varit det mest spännande i hela projektet. Nu är det bara været som ska vara med oss, så har vi de nästa 4.
Over the next few days, the other 4 turbines swiftly follow. These vast structures are now a massive 253 meters from top to bottom, more than 3 times the height of the Queen Mary II ocean liner, with 80 meters of that extending unseen below the surface. Then another world first, towing the fully assembled wind turbines across the sea. With so much drag, they can only be moved safely at 5 kilometers per hour, making the journey to Scotland take 5 days. September 2020. The Scottish town of Peterhead has a claim to fame. An hour's boat ride from the port is the only floating wind farm anywhere on Earth. The turbines have now been generating power for the town for 3 years.
We are at Hywind, Scotland, which is the world's first floating offshore wind farm. A floating wind farm can actually utilize an area like outside Peterhead, which is extremely windy, like you can see today, which shows consistent strong wind. So you couldn't build a bottom-fixed wind farm here because it's too deep, but floating is perfect.
From the surface, it's hard to tell a floating turbine from a conventional one.
The only difference is that they do have a slight vertical tilt, and you can spot that if you look hard.
Sonia Kiriko-Indrebo manages the array. It's her job to monitor the performance of the floating turbines.
We're testing for how well they perform with production, but also how the harsh environment is impacting the turbines.
The wind farm was designed to withstand hurricanes, and its moment of truth came sooner than anyone expected.
This wind farm was put in production in October 2017, and just a few days later the Hurricane Ophelia crossed and had strong winds, and we were of course really worried about what's going to happen.
As the storm arrived, the turbines were pushed backwards. If they tilted more than 10 degrees, the extra strain could have destroyed them. When the wind speed reached 90 kilometers per hour, the rotors shut down to protect the turbine from the powerful gusts. And to shield the structure from the impact of the waves, the floating base carried the whole structure safely over them.
It was a chance for the turbines to show that they can stand also in this kind of conditions. And what happened was that the turbines were performing exactly as expected.
The floating structures survived, but to be a success, they have to also prove they can generate as much power as conventional wind turbines. After 3 years of collecting data, the results speak for themselves.
When we decided Hywind Scotland, we hoped to be able to demonstrate that a floating wind farm could produce as much energy as a bottom-fixed and traditional wind farm. What we learned was that indeed it can, and it can even produce more because you can place it in an area with even more windy conditions.
This wind farm is producing more hours of power into the grid than all wind farms in the world.
In the meantime, conventional wind farms are going from strength to strength as costs continue to plummet.
Now offshore wind has fallen to a price which is less than a third of what it was 10 years ago, and which is now making it far cheaper than producing power from gas or coal or nuclear.
For 2 months in 2020, new offshore wind farms helped Britain to go coal-free for the first time since the Industrial Revolution. But as well as providing affordable low-carbon power, the offshore wind industry is replacing fossil fuels in other ways.
These industrial coastal towns were previously very engaged in the oil and gas sector. And then over 20, 30-year period, those industries started to become harder and harder to work in.
Many in East Anglia used to work in the oil and gas sector. The wind farms have given them new careers and opportunities.
One of the wonderful things that we could see about offshore wind is that we could actually breathe life back into these coastal communities. We could get those ports busy again, doing engineering work for offshore wind projects. But it was also a great thing for the offshore wind industry because we had this skilled workforce ready and willing to come and work with us and help us to deliver the potential of offshore wind.
That workforce is now building even bigger wind farms and even larger turbines. The latest prototype has 107-meter-long blades. Every sweep of its giant rotor will power a household for 2 days. Experts believe that by 2040, offshore wind farms have the potential to meet the world's electricity demands 11 times over.
Offshore wind has already shown itself to be capable of producing massive quantities of clean, green, reliable, affordable power in these huge projects that can actually be deployed quite quickly at massive scale, creating loads of local benefits. And if you look forward 10 years, almost every area with a coastline is going to be taking advantage of that coastline. And that's why offshore wind has so much potential for the electricity system of the future.